Welcoming everyone to my presentation on the history of embedded system and microcontrollers. In this talk, we will explore the advancement of an integral component of an embedded system, which is the chip, also known as the microcontroller. Embedded systems are present all around us, from our smartphones to our cars, and the heart of many of these systems present is the microcontroller. Understanding the history and development of these technologies is crucial to appreciate the incredible power and versatility they offer today. So without further ado, let's jump into the fascinating world of embedded system and microcontrollers. Now, what is an embedded system? An embedded system is a computer system that is designed to perform specific functions within a larger mechanical or electrical module. It is a combination of hardware and software that is integrated into a device or product and performs a dedicated function. Embedded systems are made up of several components, including a microprocessor, memory unit, and input and output devices. The microprocessor is the brain of the system and executes the program code that controls the system's behavior. Memory is used to store data and program instruction, while input and output devices allow the system to interact with the outside world. Now, let's talk about some uses in the embedded systems. One of the most common application of embedded system is in automotive control system. This system is used to control variety of functions such as the engine control unit, the brake control unit, and the airbag deployment. In addition, embedded systems are used in medical equipment such as heart monitors and insulin pumps. They are also used in household appliances such as refrigerators and washing machines that help us to control various functions of these units. Another important feature of embedded system is their ability to operate in real time. Real-time systems must respond to events within a specific time frame, usually measured in milliseconds or microseconds. This is critical in applications such as automotive control system, where a small delay in response time can easily lead to catastrophic consequences. Additionally, embedded systems also consume very low power. This is because they are usually implemented in devices which are very portable or on systems that are always functioning. And in order for them to not be replaced often or needed to be recharged often, there needs to be careful power management strategies and hardware design. Hence concluding, embedded systems are specialized computer systems that perform specific tasks or functions. They are used in wide range, starting from automotive control to our household appliances. The embedded system provide various features such as real-time operation, low power consumption, and securities. In the next few slides, we will take a closer look at how microcontrollers have revolutionized this field of embedded systems. Now coming to what is a microcontroller. A microcontroller forms an essential component of modern embedded systems. It is a small computer on a single integrated circuit that is designed to control specific devices or perform specific functions within a larger system. Microcontrollers have several advantages over other types of controller, which includes their low cost, low power consumption, and their small size. The microcontrollers are used in a wide range of applications, from simple consumer electronic devices to complex industrial control systems. Some common uses for microcontrollers include controlling the power supply in a computer unit, managing the temperature in a refrigerator, and controlling the motor in a robot. The capability of embedded system to operate real time is due to the presence of this microcontroller. They are designed to respond to events quickly to the input signals and also generate output signals in a timely manner. This is essential in many applications such as automotive control systems and medical devices. Another advantage of microcontroller is their flexibility. They can be programmed to perform a wide range of functions depending on the application. For example, a controller can be used in an automotive system, can be easily reprogrammed to monitor engine performance, control the brakes, and manage the airbag deployment at the same time. One of the key features of these controllers is their ability to interface with other electronic devices. Microcontrollers can communicate with other devices through a variety of communication protocols such as UART, SPI, and I2C. They can also be programmed to respond to various types of inputs, including sensors, switches, and buttons. They also need to be highly reliable and are designed to perform specific tasks that they are optimized for reliability and long-term operation. This is critical in applications where failure is not easily acceptable, especially in devices such as medical and aerospace systems. Finally saying, microcontrollers are also relatively inexpensive compared to general purpose computer. This is because they are usually designed for specific applications and don't require the same level of processing power or the memory that is needed by a general purpose computer. This makes them an attractive option for embedded system that needs to be cost effective. The development of microcontrollers has revolutionized the field of embedded systems. Microcontrollers have made it possible to create sophisticated systems that are small, low cost and highly reliable. With the continued development of this technology, we can expect to see even more advanced embedded systems in the future. Now coming in the next slide, we will see the technology that existed before the creation of microcontroller and look at its disadvantages. In the pre-microcontroller era came the TTL, also known as the transistor-transistor logic. It is a type of digital circuit technology that uses bipolar junction transistor to implement logic gates such as AND, OR and NOT. These gates are the basic building blocks of digital circuits and are used to perform logical operations on binary signals which are represented by voltage levels. TTL was first introduced in the 1960s as a replacement for the earlier digital technologies such as diode transistor logic and resistor transistor logic. TTL quickly became popular due to its high speed, low cost and simplicity, and it was widely used in electronic systems in the 1970s and 1980s. One of the key features of TTL is its compatibility with a wide range of other digital circuit technologies. TTL gates have standardized voltage levels and logic thresholds, which means that they can be easily combined with other gates in a single circuit. This compatibility made it easy for engineers to design and build complex digital systems using the TTL. However, TTL does have some limitation compared to other digital circuit technologies. One major limitation is its power consumption. TTL gates consume more power compared to the other digital technologies such as CMOS, which can lead to the overheating and reduced battery life in portable devices. Another limitation of it is the susceptibility to noise and voltage spikes. TTL circuits are more sensitive to noise and voltage spikes than other digital circuit technologies, which can cause false logic states and errors in data transmission. Finally, TTL circuits have limited fan-out, which means the maximum number of inputs that a logic gate can drive without introducing signal degradation or delays is very low. This means that TTL circuits were not be able to use in larger systems that require multiple input to be processed simultaneously. Considering these limitations of TTL and the need for packaging more components in a given space was the main motivation behind the formation of the base of microcontrollers. Now that we have a brief understanding of how TTL worked before the invention of microcontroller, we shall see the most significant invention that revolutionized the world of computing, the integrated circuits, or often shortly called the IC. An integrated circuit is a miniature electronic circuit that is created on a small piece of semiconductor material, usually silicon. It is also known as microchip, and it is this invention that paved the way for the creation of microcontrollers. Two people simultaneously had the idea for integrated circuits at the same time. It was peak time the transistor was replacing all circuits due to its small size. But as technology kept growing, even small transistors were needed, but it just wasn't feasible to connect them using wires. Scientists wanted to create everything needed for a circuit in a single blow, hence that will result in the reduction in the size of all components. First, Jack Kilby from Texas Instruments ideated to make resistors and capacitors from semiconductors, making it smaller and very easy to produce. Similarly, Robert Noyce from Fairchild realized he could bring entire circuits under a single chip. Considering Texas Instruments was also working on something similar, they called these circuits unitary circuits and got a separate patent without clashing with Texas Instruments. The planar process invented in 1959 by Gene Horney was a crucial development that allowed the creation of ICs on a mass scale. The process involved building transistor and other components directly onto a flat, thin piece of silicon, which greatly increased the reliability and functionality of these circuits. The first commercial IC was the Fairchild 101, and it was introduced in 1961. It just had 2 transistors and a resistor. However, within few years, the number of components that could be incorporated onto a single chip increased exponentially, and by the end of the 1960s, ICs with hundreds of components were available. ICs not only allowed for the creation of smaller and more powerful computers, but they also reduced the cost of electronic devices, making them more accessible to the public. Today, IC is used in a wide range of electronic devices such as smartphones, cars and medical equipments, and they continue to shape the way our lives are. The planar process, as discussed before, is the reason ICs were able to made. The planar process is also known as the silicon process, revolutionized the world of electronics by enabling the creation of ICs. Before the planar process, creating electronic components involved discrete elements and bulky circuitry. The planar process changed all of this by allowing us to create multiple components on a single piece of silicon, resulting in a significant reduction in size and power consumption. The process was invented by Gene Horney in 1959 while working at Fairchild Semiconductor. It involves doping a silicon wafer with impurities to create specific regions of P-type and N-type semiconductors. After this, a layer of oxide is grown on the surface of the wafer and then followed by the application of a layer of photoresist. The photoresist is then exposed to light through a mask, causing it to harden in certain areas. The unhardened areas are then etched away, leaving behind a pattern on the oxide layer. The oxide layer acts as a mask for the subsequent doping process, creating regions of different conductivity on the silicon wafer. This process allowed for the creation of small and more complex integrated circuits than what was previously possible. It also paved the way for the development of microcontroller and other advanced electronic components that have ubiquitous in modern technology. The planar process is still in use today, but it has undergone many refinement and improvement over the years. It remains an essential part of the semiconductor industry and has played a critical role in the development of modern electronics. Now, here I shall introduce you to the Intel 4004. In 1971, the Intel Corporation introduced the world's first microprocessor, the Intel 4004. It was a 4-bit CPU with a clock speed of 740 kHz and was designed for use in calculators and other simple computing devices. The Intel 4004 was a significant milestone in the development of embedded systems. Prior to its release, electronic devices were built using discrete logic components such as transistor, resistor and capacitors. These devices were often large, bulky and consumed a lot of power. The Intel 4004 had changed all of that. It was a single chip solution that was small, lightweight and consumed very little power. It allowed for the creation of new types of electronic devices and sparked a revolution in the electronics industry. The Intel 4004 had a 4-bit data bus and a 12-bit address bus, which allowed it to address up to 4 KB of memory. It also had a total of 16 registers, including a program counter, stack pointer, and 4 general purpose registers. While the Intel 4004 was not a particularly powerful processor by modern standards, it was a major breakthrough at the time. It paved the way for development of more powerful and capable microprocessors and helped to launch the embedded system revolution. Today, the Intel 4004 is regarded as a landmark achievement in the history of computing. It has demonstrated the power and potential of microprocessor technology and paved the way for the development of the devices that we use every day. Next comes the TMS-1802NC, widely regarded as the first microcontroller. Semiconductor technology had made it possible to replace the hundreds of intricate small metal and plastic parts present in many devices. One such device which needed computation in the early days was the calculator. The semiconductor initially replaced the hundreds of transistors and diodes present with fewer and fewer integrated circuits. Companies such as North American Rockwell, Microelectronics, the General Instruments and Texas Instruments were early players in the multi-chip calculator market. At the initial stage, a few dozen integrated circuits were needed to replace hundreds of transistors and diodes. But as the technology grew more and more, it took fewer and fewer ICs to build a working calculator. By 1968, IC-based calculator design had largely supplanted the transistor-based designs. The endpoint was very clear. Eventually, semiconductor manufacturer would reduce the electronic guts of a calculator to only a single chip. Now, focusing on the Texas Instrument, mainly on its MOS department. The business for the MOS department in Texas Instrument was to make custom calculator meeting the requirements for various companies. Many companies come to TA with a specific set of requirements, and making note of all of these requirements, Texas Instrument would convert those specifications to a chipset, normally including 4 to 6 chips, to execute or implement the specification for popular companies such as Canon, Olympia or Olivetti. For these companies, it was amazing that TI could provide the ultimate service of compressing so many units into just 4 or 5 chips, because the previous technology would have needed hundreds or 200 chips using the TTL technologies. Hence, the business were going very great. Though the requirements of the project from various companies differed in detail, the overall principle and function was very identical. So the engineers were really tired of doing these monotonous projects again and again. They were working for long hours, and they felt there should be a better way to accomplish these projects, and they should be other side, and then the functional blocks of the circuitry on the other side. Now, Gary had a thought saying that if he had enough bytes of data storage and enough bytes of program storage and also specific bytes of keyboard scan interface, then all of that would cover the specification he knew about. As a result of this thought came the first TSMS 1802NC, which is widely regarded as the first microcontroller. Now, while it is regarded as the first ever microcontroller, it needs to be noted that it is not a very general purpose compared to modern microcontrollers. Its main aim was to satisfy the microcalculator market, and it was not considerably to be used in general purpose computation. After this comes the TMS 1000, aimed with the knowledge that the microcontroller could serve multiple markets with the same programmable silicon. If the silicon could be engineered to be sufficiently general, TA had applied what it had learned from the family of devices it built originally from the programmable calculator chip to produce its first line of general purpose microcontroller, the TMS 1000, in 1974. The TMS 1000 family used masked program ROM. Hence, once the user had debugged a program ready to be committed to production, it would send the program to Texas Instruments, who would then make a special mask to program the on-chip ROM. The ROM could not be altered in the field. The contents were fixed by the patterns laid out on the chip by the manufacturer. While this process had an initial high cost, the production cost was very low, making it suitable for high volume products. Say more than a few thousand items can be sold per year. All internal data parts of the processor were 4 bits wide. Programmed ROM and data RAM were separately addressed as in a Harvard architecture. This became a typical characteristic of microcontrollers by many other manufacturers. Next come the Intel MCS48. Intel had announced the first commercially successful microprocessor, the 4004, in the late 1971s. By 1974, Intel had introduced 4 microprocessors, including the 4-bit low-end 4004, the upgraded 4040, the 8-bit 8008 and the 8080. Intel's 4-bit 4004 and 4040 microprocessors were used primarily for embedded control applications. However, Intel has no longer had the microprocessor market to itself. There were various other semiconductor vendors that has been competing the microprocessors by 1974. And even worse, the 4-bit TMS 1000 microcontroller family introduced by Texas Instruments, which had put a 4-bit CPU, RAM, ROM and input-output circuitry on a single chip, had simplified design and cut the cost of processor-based control significantly. The introduction of this TI's processor family got the attention of several customers due to the introduction of various other instruments, especially due to the 4-bit TSMS 1000 by Texas Instruments. Now, in order to regain the market, they needed to introduce their own microcontroller, and it was decided that 4-bit microcontrollers were very slow and they need to make an 8-bit microcontroller. The need of an 8-bit microcontroller and the desire of Intel to regain the market resulted in the production of Intel MCS48. It boasted a 74 instruction set with about 64 bytes of RAM, which was just enough for them to advertise themselves properly and regain the market. Now, considering microcontrollers, apart from processing power, memory also plays a very crucial part. The history of the ROM dates back to the early days of computing, when the first electronic digital computers were being developed in the late 1940s and the early 1950s. The earliest form of ROM was a magnetic drum memory, which was used to store large amounts of data. The magnetic drum memory consisted of a rotating drum coated with a magnetic material that could store data as magnetic spots on the drum's surface. In 1960s, the semiconductor industry revolutionized the way computers were built and ROM chips were developed. These chips were made of simple semiconductors such as diodes and transistors that could store data using an array of electronic switches that were programmed to represent zeros and ones. The first ROM chips were designed to store small programs that could control the computer's operation. The early ROM chips had limited storage capacity and were relatively slow compared to modern memory technologies. They were also expensive and difficult to manufacture, which limited their use in electronic devices. Despite these limitations, ROM chips quickly became an essential component of early electronic devices such as calculators and game consoles. These were used to store the basic operating systems and game softwares that control the device's operations. Next comes the EEPROM, or the Erasable Programmable Read-Only Memory. Was a revolutionary memory technology that played a very significant role in the development of early electronic devices. The EEPROM was first introduced in 1971 by Intel Corporation. The technology allowed for the creation of a read-only memory chip that could be programmed and erased multiple times, which was a very significant improvement over the MOS-ROM technology that was commonly used at that time. The first EEPROM chips were made using a simple technology that relied on the use of ultraviolet light to erase and reprogram the memory. The chips were made of a grid of memory cells, with each cell containing a transistor and a floating gate. The state of each memory cell was determined by the presence or absence of an electrical charge on the floating gate. EEPROM chips could be programmed by application of a high voltage to the control gate, which allowed electrons to tunnel onto the floating gate, creating a charge. The charge on the floating gate could be erased by exposing the chip to ultraviolet light, which caused the electrons to escape from the floating gate. EEPROM was particularly useful in the development of embedded systems, which are computer systems that are built onto other systems such as cars or medical equipment. The system required memory that could be easily reprogrammed as needed, and EEPROM provided a solution that was both cost-effective and reliable. Next comes the EEPROM, or the Electrically Erasable Programmable Read-Only Memory. It was a non-volatile memory technology that allowed for data to be stored and erased electrically. It was first introduced in the late 1970s by George Perlegos, a Greek-American engineer who was also working at Intel Corporation. It presented a significant improvement over the existing EEPROM technology, which required the use of ultraviolet light to erase the memory. EEPROM allowed for the creation of non-volatile memory that could be easily programmed and erased electrically without the need for special equipment. This was a significant advancement in the field of microcontroller, as it allowed for more flexibility in the design and development of the embedded systems. In order to erase the data stored in a EEPROM, it must be removed from the circuit board and then exposed to ultraviolet light for a specific period of time. This then makes it ready to be flashed with a new program. This is a very time-consuming and inconvenient process. In contrast, EEPROM memory was be able to erase and reprogram electrically. This allowed for a faster and more convenient data storage and retrieval, as there is no need for us to remove the chip from the board. EEPROM was particularly useful in the development of microcontrollers because it allowed for the creation of non-volatile memory that could be easily reprogrammed as needed. This made it possible to create microcontrollers that were more flexible and adaptable to changing requirements. Flash memory was first invented in the mid-1980s by Dr. Fujio Masuoka at the Toshiba Corporation. The technology represented a significant improvement over existing memory technologies, particularly the EEPROM, as it allowed for larger memory capacity and faster access time. EEPROM memory uses a series of transistors to store data, with each transistor representing a single bit of data. In order to rewrite this, electrical charge needed to be applied at the transistor, which will change its state and store the data. Flash memory, on the other hand, uses a special type of transistors called floating gate MOSFET to store the data. Each transistor can now store multiple bits of data, which allows for greater data density and storage capacity. To write data to a flash memory, a high voltage is applied to the transistor, which causes an electrical charge to be trapped in the floating gate. To erase the data, a high voltage is again applied, which removes the charge and resets the transistor to its original state. Compared to EEPROM, Flash PROM is very faster to read and write. And also, EEPROM was needed to be erased only at a single bit at a time. In contrast, flash memory was to be able to erase and rewrite blocks of memory, which proved to be very faster. Now, as technology evolved, flash memory became more widely used in the development of microcontrollers. The ability to easily reprogram the memory made it possible to create microcontrollers that were more flexible and adaptable to changing requirements, making it an ideal memory technology for embedded systems. Today, flash memory is one of the most widely used memory technologies in the field of microcontrollers. It is used in a wide range of applications, from simple embedded systems to complex automotive electronics. In addition, newer memory technologies such as NAND and NOR flash have evolved from the flash memory, providing even greater flexibility and performance in the development of microcontrollers. Over the years, microcontrollers have significantly evolved, and modern-day microcontrollers have become highly integrated systems that offer a wide range of features and capabilities. Modern-day microcontrollers have advanced mainly in the following areas, such as getting integrated with input-output peripherals and communication interference. Modern-day microcontrollers have become highly integrated systems on a chip. This integration has reduced the overall size and power consumption of the system and makes it easier to design and develop embedded systems. Modern-day microcontrollers, compared to their predecessors, offer very high performance processing capabilities and handle complex tasks and real-time processing requirements. They are also nowadays included with wide range of features such as analog to digital converters, pulse width modulation generators, timers, and then communication interfaces, providing flexibility and scalability in their design. New innovations that come in the microcontroller today include improving the hardware security features, artificial intelligence accelerators, and machine learning capabilities. Along with this, the real-time operating system and wireless connectivity, which are an integral part of IoT, are also being implemented in the microcontrollers. Overall, the advancement in modern-day microcontrollers have made them an essential component in various industries, and the choice of microcontroller for a specific application depends on the specific requirements and constraints of that application. Finally, I would like to just talk about few industry leaders that are present in the microcontroller and semiconductor industry. First, we have the Texas Instruments. It is an American semiconductor company based in Dallas, Texas. They offer a wide range of microcontrollers with different features. Their main product include the ARM Cortex-M and the MSP430 families. They are well known for their low power consumption, high performance, and integrated peripherals, making them ideal for industrial, automotive, and IoT applications. Next comes the microchip technology. Microchip is an American semiconductor based in Chandler, Arizona. Microchip technology offers a broad portfolio of microcontrollers, including 8-bit, 16-bit, and 32-bit families, with various features such as integrated analog, digital, peripheral, and communication interfaces. Their microcontrollers are again widely used in automotive, industrial, and consumer applications. NXP Semiconductor is a Dutch-based semiconductor company which has its headquarters in Eindhoven. One unique feature of NXP LPC microcontroller is their support for their patent FlexCom interface technology. This allows one to use multiple communication protocols on a single interface. This allows for a greater flexibility in designing and implementing communication interfaces for various applications. Then comes STM Microelectronics. STM Microelectronics is a multinational semiconductor company based in Geneva, Switzerland. The unique feature of their STM32 microcontroller is their support for functional safety, making them suitable for applications that requires compliance with safety standards such as ISO 26262 and IEC 61502. ST microelectronics STM32 microcontroller also have built-in hardware security features including secure boot, secure firmware update and hardware cryptography acceleration, making them suitable for applications that require high level of security. Finally, Renesas Electronics. Renesas Electronics is a Japanese semiconductor company that was formed through the merge of NEC Electronics and Renesas Technology in 2010. It has a very strong presence in the automotive industry, providing microcontroller and solution for advanced driver assistance system, vehicle electrification and infotainment systems. They have a focus on security and offers microcontrollers with built-in hardware security features including secure boot, hardware encryption and tamper detection. Along with this, they also offer a range of analog and digital components that can be used alongside their controllers to provide a complete solution for a wide range of applications. These 5 are just a few examples of top microcontroller companies, and there are many other notable companies as well. Since their inception in the 1970s, they have revolutionized the way we interact with electronic devices and have become an essential component in various fields including industrial automation, robotics and IoT. Today's microcontrollers are more powerful and efficient and versatile than ever before, and they continue to shape the future of technologies. I hope that this presentation had given you a better understanding of controllers and their importance in modern electronics. Thank you for your attention, and we look forward to see you again.